Today we're going to talk about electrical system testing, adjustment, and measurements in the context of using our electrical troubleshooting board. Now, what we're going to do is we're going to notice the system doesn't work, and then we're going to start measuring different parameters to try to see like what exactly is going on in that system, and then we're going to make adjustments to make it work. Okay, so when we hook up to our tester, we're going to test for three things basically at any one point in time. You're going to have voltage, you're going to have amperage, and you're going to have ohms or resistance or continuity. All kind of like not quite the same thing, but like they get used interchangeably a lot of times. So on our tester, this is just to orient you as we kind of proceed with this video, is that you have voltage over here, and the wavy line will always mean AC. So, all right, so alternating current goes up and down, so the wavy line goes up and down. That's just your sine wave. It's all AC, up and down, up and down, up and down. So remember, V is voltage, wavy line, AC. Notice it says VAC up here. So if you ever get confused, you can just flip through there, and this multimeter at least will tell you. A lot of them don't. This is a fancier one. The M is basically millivolts. It's just divided by 1,000. The movement, non-movement line, it's a solid line with little dashes underneath it, means DC. So you have voltage with DC, and then you also have millivolts DC as well. Now, when we start doing your resistance, we start looking at ohms. This is the setting that we're going to be on. Always have your alarm set up so that way you can hear whenever there's continuity. See? Always do that. That'll make your life so much easier because you can hear what's going on. You don't have to see what's going on. And a lot of times when you're doing this kind of work, your head's going to be in some weird spot that you can't just go and just look at whatever you're saying or whatever you're trying to say. And if you absolutely have to, most times it's really good to be working with a buddy who can read it for you. And then finally, amperage. Now, whenever we do amperage, we're going to switch our lead over so that way it's fused. So that way if we tie into like a really high amperage, it doesn't blow the meter up. And if anything, it'll just blow the internal fuse up. But yeah, so we have millivolts AC, microvolts AC on that. Now I'll tell you, like I've troubleshot a lot of airplanes, and you can go a long way with continuity. You can go a longer way. Well, you can go the longest way with continuity. You can go a long way with voltage. Checking amperage is something that only happens every once in a while. Sometimes you have to have it. A lot of times it's going to come down to you have some sort of power generation problem. It's not producing enough power. It's producing the right voltage, but it's not producing the right amount of push on the amperage side to power whatever it is. So that could be a thing. So just know that kind of going forward, that like if something is dying, maybe it's on the amperage side, but most of the time you're going to live in the continuity world or the voltage world. In the voltage world, you can start doing voltage drops, and you can find a lot of interesting things that way as well. But yeah, so that is your measurement and testing kind of orientation right there. So let's get on and we'll look and see what it looks like in real life as we employ it. All right, so in our example today, we don't have an avionics buses on. We've got main power on. We have the avionics master turned on, but if you notice, there's no light coming on whenever it's supposed to. So that's what we're going to troubleshoot by taking different measurements to try to figure out what's going on. Okay, so the first thing that we're going to want to do is just safe the system. Notice the power is still on, so we're going to take the power off. Power's off there. And then we're going to disconnect the battery that's over here. All right, so one of the first things that we can do is to just see if we're getting continuity through that light. All right, so we see that we're getting 48.85 ohms. So we're showing that there's continuity through there, but it's really, really high. But we would expect that because there's a light bulb there. Kind of a good way to check that is just simply remove the light bulb. And we notice that all of a sudden we have no continuity. If you can see that from where you're at, we'll turn the alarm on. That it's saying that it's an open line, that there's no continuity on there. We put it back, all of a sudden we get something. All right, so it's a good kind of like learning moment is that, like, don't just take your first check for granted. Shoot through the wire, and if it's ringing, try to see if you can disrupt it on purpose and then put it back. Even if it's just simply like just taking the lead away and then putting the lead back on to determine that you're actually getting continuity. So right now we're reading, saying about 160 ohms or so, and so we know that we're getting continuity through there. So now let's check power. All right, so we've reconnected our battery. We're gonna come over here and we're gonna say master coming on. We have power. Our avionics master is coming on. We still don't have a light. Still getting continuity through it. Let's go over and let's check, see what we get for power. That's supposed to be DC power. No power going through the light at this point. So that now we know we have a problem. So let's start trying to work our way back and try to see if we can find where the power disruption is. Kind of a good rule of thumb whenever you're doing this type of work is to look and see what all is actually working, so you can quickly eliminate some things. So in this situation, we see that we've got power going on to the main bus. We don't have the alternator on, so we don't have to worry about that, but we do have battery volts, so it's not an under voltage situation. We have power going on to the lights. We know that circuitry works, so it's really just going to be localized into our avionics bus over here. Before we get too crazy into it, let's do a bulb swap. Make sure that the bulb isn't the problem. When we look at it, we pull it out and look at it, we see that bulb looks like it's good, but we don't know that for sure. But we can see that this little green bulb right here for our nav lights is working. Let's put it on there and see if it's... Okay, so it doesn't work, but let's check this bulb. Okay, that bulb works. So we know the bulb isn't the problem. At this point, we know that it's just, for whatever reason, there's no power to the socket. If there's no power to the socket, then that'll be the case. And we can verify that there's no power to the socket simply by pinning off to ground. So we're on our ground bus now. We're on 12 volts DC. Pull the bulb out. And we're just going to pin that right there. And notice there's no power. So now let's just start thinking through where else could we have lost something. So if we know that there's no power going to the light bulb, and we want to find where that power should go or should be, let's just start doing some continuity checks and just kind of mapping out where things should be. Now, this is normally where we would have a wiring diagram, and then we'd start to work our way back. And you'll do that in class with the actual aircraft, but for the trainer, we don't have that, but it's easier to display this on video, so just bear with us. All right, so we're set to mega ohms. We have continuity, or we have ohms selected. We have the auditory alarm on. We're gonna check it. So we know that our meter works, and that's something that you always want to do, is always make sure that your meter works before you get to going, or else you might end up accumulating a lot of data on a system that really just says, hey, your meter's broken. And then we're going to, look, we have a wire number here that says R3B20. That's Romeo 3 Bravo 20. So we're going to go down here to our avionics relay. Let's see if we can adjust a little bit. So we're going to go down here to our avionics relay. We see that we have this bus bar here, and we see that R320 comes in right here. All right, and so we know that we have continuity from here to there. And so we're going to go down here to our avionics relay. We know that the relay actually has continuity through it. So power has to be dropping off somewhere in there. So if the relay works, and then then we know that the rest of the avionics systems work, then we can pretty well deduce that somewhere between here and here is the problem. The question is where. Now, I happen to know that there is a disruptor circuit right there that the switch is turned off right now. That's why the light's not coming on. But we wouldn't know that on an aircraft. This could simulate any number of things that could happen, to include broken wires, corroded connectors, disconnected components, all kinds of things that could happen to create this sort of situation. So let's go back here and we'll reset our all right, let's put it on DC volts. Notice that there's no voltage here either. Even whenever we've gotten continuity through there, we know that power should be coming through the relay into this distribution bus and then out to the different components, and we're not seeing it. Okay, in this scenario, our right nav light is not working, and so we're going to do some measurement to try to test and see what's going on with it. Now, the first thing that we would want to do is simply just change the bulb out. So we notice that this bulb is the one in question. We know that this one is currently working. We put the working bulb back into the socket that is not working, and it doesn't work. So leading us to believe that it's the socket. But let's verify, and we'll put the green bulb at the tail light, and we see that bulb works just fine. When we swap them back, it returns to its original condition, meaning that we know that socket now is not working. So let's take some measurements. First off, let's just see if we have power going there. So we're going to need to go to a ground. So we have a ground bus right here. We're set up on DC voltage because we don't have AC going, it's just DC volts. Turn the light on, maybe you can see it a little bit better. All right, and we're just going to pin right there at the junction. We see that we have no power going to it. So you can see that there's no power going to that light bulb, so that we have a power problem. Just to be thorough, let's make sure that we actually have a good continuity to ground. So we're going to leave our meter hooked up to the ground bus. We're going to watch the meter so that it's open. And then we're going to just pin to the socket, because most light bulbs, especially the incandescent ones, they ground through the socket. So we're seeing that we got 4.27 ohms through that. So that means that we have a power problem somewhere in our circuit. All right, now let's say like if we traced those power failures back to there was no battery power, and that's a very viable reason why you wouldn't have power, and it happens pretty often. So let's review aircraft batteries, remembering that there's 3 types of batteries out there. There's lead acid, there's NiCad, and there's lithium ion. Now lithium ion we won't really mess with because they're only found in a very few, very elite, very top tier aircraft, and there's just not that many of them out there. Whenever you camp onto a maintenance program that has to deal with those, there'll be training that you have to do, there'll be certifications you have to do, so that way you understand all the implications of a lithium ion battery. The ones that you will deal with, especially in any other facet, minus general aviation, and when I say general aviation, I'm talking about like older recip type aircraft, like the ones behind me. You'll almost always have NiCad batteries in there. NiCads generally produce a more stable power band. They are a little bit easier to maintain, even though if they get super low, they can cause a lot of problems because they are kind of advanced. And they require specialty chargers. You can't just like throw them on a battery charger you can get at Walmart or something like you can with lead acid. But that's a NiCad battery, and you'll deal with those on the Lear. You'll be schooled up on them as we remove and install and check and do all that kind of stuff with them. The ones that the lead acid batteries, though, they basically break down into 2 camps. You have sealed lead acid batteries, and those are batteries they're all just like the ones in your car. Your lead acid batteries nowadays that are sealed, you don't have to worry about servicing the water. or doing anything of that nature. It's literally, is the battery charged or is the battery not charged? The end. And if you end up having to replace, or you can't get one to charge, you just replace it and you go on about your business. The ones that are not sealed, you'll end up having to take your hydrometer and check and see if for one, is there water in there? Number two, is there what's the specific gravity of the water, and that'll indicate whether or not there's enough electrolyte in the water to actually make the battery work. And so you'll just simply add either electrolyte or you'll add water to get the right balance of electrolyte in there to match the specific gravity of that battery. So there's our battery review. Now let's think through some other interesting dynamics that come with batteries and that could help your troubleshooting. All right, so let's go through the 8083's battery troubleshooting table, and we'll just kind of talk through it, and hopefully get some pictures and things on there to kind of help lend to your mental model of what some of these things will look like. All right, so we're going to start with the first one, the apparent loss of capacity. I mean, the battery just simply doesn't seem to be charged. It's not seeming to produce what it used to. This happens, especially with older batteries. This is where the older lead acid batteries actually shine, because you can pull them out, put new electrolyte in them, you generally kind of get them back. However, if you have a NiCad battery that's doing this, most likely that's the end of that battery's life, and it'll have to go get completely rebuilt, or it'll have you just need to get a new battery. Same thing with the sealed batteries. There's not a really good way to boost them back up, so it's just time for a new battery, and you just change it out. All right, so complete failure to operate. That basically means that the battery is just not coming online. You flip the switch and nothing happens. Almost every single time it means that battery is disconnected. Either someone has disconnected it to do some maintenance, or maybe the airplane was sitting up for a while and they didn't push it back in, or somebody did connect it, but then a terminal is broke loose. That's especially on older airplanes that don't have a really robust maintenance program that support it. The broken lead is where you're going to want to start your request for answers. Okay, excessive spewage of electrolyte, meaning the electrolyte's dumped everywhere. Now the 8083 will tell you that the battery got too hot, got too overcharged, and those are all things that if you overcharge a battery, it can boil the electrolyte, and the boil turns to steam, and that steam has to go somewhere and it'll spew out. So that can happen. And it can also happen with NiCads as well. Lithium-ion batteries, they just explode and burn up. But more often than not, from what I've seen, is that most of the time that battery wasn't secured properly, and then somebody got into some sort of aggressive flight profile, and the battery rolled out, and then the electrolyte went all over the place, and so then the whole back end of the airplane's getting corroded out. Just know that that's a potential. But any of those other conditions that they say, like a damaged cell, that's completely possible. It could potentially happen. However, it is somewhat rare, and at least in my experience, most of the time it's going to be somebody just didn't tie it down correctly. Okay, so failure of one or more of the cells to rise to the required 1.55 volts at the end of a charge. It's a negative electrode, not fully charged, cellophane separator damaged. Basically, you have a bad cell. That happens, especially on NiCad batteries. You'll get bad cells, and so you'll have to end up either changing the cell out, which is the most likely situation. And they're built that way. You pop the lid open, and there's just I think it's like 9/16 bolts, and then you can slide the cell out and put a new cell in. You can also service them in certain scenarios, but most of the time, what you're going to do is you're going to send this battery off, and then you're going to get a new one and put it in there. Okay, foreign material within the cell case. So meaning that like you poured something into the battery whenever you were servicing the battery, and that happens as well, especially if you don't keep a clean shop. Remember, always keep a clean shop. There's a rule, always be Nolan. Nolan means to put everything in like a 90-degree orientation pattern. Always be Nolan wherever you go. Always be cleaning up. Like the cleanest shop will have the cleanest maintenance, bar none, no matter what. The best way to prevent getting stuff into the battery is making sure that you're in a clean environment. If you're in a clean environment, you don't have to worry about it. There's a reason why they build satellites in clean rooms, because no one can work on them up there. So you have to keep the FOD to the minimum. Okay, frequent addition of water. So this is a kind of an indicator that you got a battery that's about to die. The cells are out of balance, damaged O-ring, meaning that the cells are leaking. A leaking cell, the cell itself is leaking, or a damaged vent cap, so that when the airplane rolls, it all ends up going out that way. Once again, most of the time, it's just cheaper, safer, better to just replace the battery rather than trying to work on the battery. But if you're in a situation where you can't do that, this is something to pay attention to. If you're having to constantly service that battery, something is going wrong. That, like, it's not sealed correctly, it's leaking out somewhere, or whatever the situation is. That water should be pretty stable. Like, you shouldn't have to add it more than like once a year, if that. And so like to have to put that on a troubleshooting chart is troubling. Anyways, so corrosion of on the top hardware, acid fumes or spray or other corrosive in the atmosphere. So this actually is probably the most common battery ailment. And it's not really anything to do with the battery. It's that, like, it's just the corrosion triangle coming to bear. You have dissimilar metals that are usually right there. You usually have like copper leads on a steel battery lead, and you have an environment where, especially if you're around salt water, you're going to have salt in the air. But anywhere you go, even out in the desert, you're still going to have certain kind of trace levels of moisture inside the air. So all it really needs is that moisture to start to create the pathway to create corrosion. And so, like, you're going to end up having to clean battery leads on a regular basis. Now, if it's excessive, there may be something going on there. But like, some corrosion on something that has electricity going through it to a very minimal level is pretty common. It's not anything that's just out of control. Okay, discolored or burned in connectors or internal connectors. That means a dirty or loose connection, loose connections, improper mating of parts. Now, I've actually seen aircraft catch on fire from this exact thing. The thing is that, like, if you think about things like a wire, right? If you have a lot of power going through a wire, and that wire is just super thin, well, that wire is going to get super hot, because you have the same pressure, the electromotive force on one side pushing everything to go through this really skinny wire. The only way to do that, only way to make that work, is if the electrons inside that wire start going really fast, because they have to get out of each other's way. Remember, it's like people in a concert pushing forward, and like the only way to get everybody out is to send people through one door, and the only way to get people out at a reasonable pace is just everybody goes really fast. They just get out of the way, go. Whereas opposed to if you had like a really big wire and you have the same force, well, it's like having a bunch of doors open, or a huge door open for everybody to kind of leave the concert so they can easily go on out. And so they don't have to go as fast. If they don't have to go as fast, there's not as much friction. And so in the situation where you have like burnt leads, that means that lead is either sitting on there cockeyed, it's not making full contact with the battery, there's something that's not 100% somewhere in there causing the path of electricity to squeeze down. And as it squeezes down, that current starts to go up, and that temperature goes up with it. As that happens, that will cause burnt ends to happen. And like I said, I've seen fires from this exact scenario. A guy didn't torque down these power leads, and they were sitting cockeyed, which effectively took that power lead from having this amount of available space to transmit electricity to maybe half that, because whereas they were sitting, so if you imagine like this is your lead, and then you have like that contact that's sitting on top of there, if all of a sudden it's sitting like this, how much surface area can that electricity actually go through? Just the corner, rather as opposed to the whole thing. That's effectively like attaching a really small wire to it, and that increases heat, and heat eventually you get to a certain point where everything has a flash point, and it'll catch on fire. Okay, distortion of battery case and cover. You have an explosion. So essentially, if you look at the case, so a lot of especially general aviation aircraft, most aircraft have like a case the battery goes into, and then it's sealed on top of that. The reason being is that way if something happens with that battery, it's contained and it'll just go everywhere. So if you go up to one of those battery cases and it's all like woppy jawed, that means that something exploded, which meant the battery probably got too hot, or you have like some sort of like weird off gassing, vent plug is plugged. There's no telling. There's all kinds of things that could potentially happen. So while one word on story on lithium ion batteries. They are really bad about thermal runaway. Like in last semester, we talked about the Boeing 787 having like all those battery fires, because they were the first people to try lithium ion batteries, and I don't think anybody really appreciated how dangerous they could be in the right circumstances. So this is kind of a lesson learned for all of aviation. I'll tell you, I've seen drones do this, where drones will use lithium-ion batteries because they pack a lot of punch. They have a nice, smooth power band for an electric, airplane, and then they also are very, very light. And so you'll get these little lithium-ion batteries that get plugged into drones. Well, we had one in Iraq that we pulled out and set on a chair, because when we pulled it out, we noticed that, man, this thing feels warm, and it was like not its normal brick. It was like expanded a little bit. Right, man, that's weird. So we took it and set it off in this chair, and within a few moments, it exploded, caught on fire, and burnt the chair to the ground. So that's something to always be worried about with lithium-ion batteries. Like thermal runaway in a lead-acid battery, probably not going to happen. Thermal runaway in a NiCad battery, a little bit more common, can definitely happen, but it's not that common. Thermal runaway in a lithium-ion battery, be really serious. So like be really conscious of those, and know that there's circuits in place to catch these things as they happen.